So welcome back. In this subsection, we'll look at the overview of the algorithm and the first two steps of how to build a suffix array in linear time. As the title says, building the suffix array is the same as sorting the suffixes lexicographically. So this is also sometimes called just suffix sorting. Before we discuss this slide, I just want to point out that the linear time sorting of suffix arrays is a fairly recent result. It's all in this millennium, which, I mean, given that it's fairly fundamental, I find that always a bit surprising or astounding. So the algorithm we'll present is from a paper from 2003. So you were all alive when that happened, and this is different from some of the other results, which stuff from Unit 2 dates back at least to the 50s, 60s. Some of the other things are in between. If you go back to that time and look at what the computers were like, they were vastly different and much smaller. But 2003, come on, that's our age, right? So the results are quite recent. I think they're remarkable in beauty in that they have these very beautiful insights that make the algorithms tick. But also, none of the little tricks by itself is really impenetrably hard, as you will hopefully see. It's all just little tricks, but you need to add quite a few of them together before this all makes one round picture. So that's kind of my motivation for you, and also my warning. Bear with me for a while. We will take most of today for getting through this algorithm, but each individual step should be doable with a little bit of caffeine, maybe. Before we discuss the actual algorithm to construct the suffix array, it's convenient to introduce the inverse suffix array. And that really is the inverse in the sense of a permutation. So the suffix array here, that's L. It's the same example, so you will see these numbers pop up on many slides in the next hour. The suffix array, again, tells you the rth entry is in sorted order, in this lexicographic order of the suffixes. What's the starting index of the rth suffix? So for example, the fourth smalls, the one with rank 4 starting at 0, for this string is the entire text. No, I lied, almost the entire text. It's the suffix starting at 1, obviously, because the strings also start at 0. Now, the inverse suffix array is the inverse permutation of this list of numbers. Notice that the suffix array always is a permutation. Every number between 0 and n occurs exactly once. It's the numbers 0 to n somehow jumbled. And so you can ask yourself, if I look at, that's what's spelled out here, if I look at what is at the position, well, where's the 7? The answer is position 2. So you would like an array that gives you at position 7 the entry 2. That's the inverse suffix array. There's nothing fancy in this concept. It's very easy to compute. If you have 1, you could just iterate over it and fill the other by inverting the index and the value. What I'd like to do with this slide is give you a few mnemonics to not mix those two up. So I named the suffix array L for leaves, because that is the leaves from left to right in the suffix tree. And the entry in the suffix array is the suffix, and the suffix is the same as its starting index. The other thing, the inverse suffix array R, I called it R because it's the rank array. It tells you for the suffixes in text order, right? This is suffix starting at 0, suffix starting at 1, and so on. What is its rank in sorted order? So the one starting at 0, the entire text, is rank 6th in the sorted list. Just a little caveat again, we start with 0, so the ranks are also 0 based. Okay? Relatively easy concept, but try to keep those in mind. Another mnemonic is R is for going right and L is for going left in this picture. I think it's a fairly natural thing to say in this picture, we start on the left with the text with the suffixes in text order, where you just start with the entire text and then you leave off one more character. That's very easy to build. And then going to the right, you sort them. So here you have the same strings, but sorted lexicographically. If you've done that, then R takes you to the right. If you have an entry here, the 0th, it tells you where you find it on the right, and L is the opposite. Okay? So that's just a few ways, hopefully helping you to keep in mind which one is which. But the slide's always there for you to look it up again. And this is a question that accidentally you've seen last time already, but this time you really know what we're talking about, so I'll just ask them again. So this is just reinforcing the new knowledge. Again, quite a lot to read, so I'll give you a bit more time. Maybe a few more than 19 is possible. All right, I'll leave it open, but here's the distribution of answers. Quite a few things got quite a few votes, but also quite a few of the answers are correct. So let's just briefly go through these. The last four are just the last thing I said in the previous slide. That's different ways of hopefully remembering what L and R was. I found these helpful. And then these statements are just mimicked for L and R. So again, L is the leaves in the suffix tree from left to right. And I would like to, L stands for left, but in the sense of this previous picture, going left from the sorted suffixes back to the text, the suffix in text order. L also lists the starting indices of suffixes in lexicographic order. So both of these statements were true for L and not for R. The true thing that you could have said about R is that R gives you the rank of the suffix starting at a position. So it's the rank array. That's why it stands for rank. All right. So I said before, if we want to have any chance of sorting suffixes in linear time, worst case or not, we have to exploit the fact that these are not arbitrary strings, but they are the suffixes of one text. If you sort arbitrary strings, you can't break this n log n barrier, and in many cases you can't even quite achieve that because you need to compare all the common prefixes. But we do have a text and all its suffixes, so we can sort it more efficiently. And here's this algorithm that we'll discuss. It's called the DC3 algorithm or the Skew algorithm. If you want to know why these names are there, you will have to read the additional reading. It's a recursive algorithm, and it does 3 simple steps. And that together will sort the problem. Remember, we're sorting. It's all about sorting the suffixes. What we'll do is we first recursively sort 2/3 of the suffixes. And which ones? Well, we sort those that start at positions 2, 1, 2, so we take those that start at position 1 and 2. We don't take the multiples of 3. So then we take 4 and 5. And so that's how you take, out of every 3 consecutive ones, you take 2. Okay? So we take the suffixes that start at these positions that I marked in this. Another way to say it, all the indices that are not equivalent to 0 modulo 3. These we sort recursively, and we'll show in a second why this is fast enough. For now, I'll just throw these steps at you. For each and every one of these steps, there will be more details later. Okay, this is just a big overview for now. The second step is all the suffixes we left out, those that start at multiples of 3. We still have to sort them somehow, and we can infer their order from these ones that start at positions 1, 2, modulo 3. So I'll abbreviate with R12, the rank array for this subset of suffixes, those that start at these positions, and then R3 is those that start at multiples of 3. Could have called it R0, but it's the same modulo 3, I guess. And so it turns out you can induce this rank array R3 from the other one, and we'll see how. And then we have two sorted lists of suffixes. Remember, suffixes is in a sense just strings. So we have 2 sorted lists of strings. So what we can do with them is just merge them, and then we get the entire sorted list. And that's the third step. Again, to make this fast, we'll have to make proper use of these rank arrays, and you'll see in a second why or how. Now, this smells a little bit like merge sort, but there's a key difference. It only does 1 recursive step. It only recurses on 2/3 of the lists, unlike merge sort, which split the list in 2, but it recurs on n elements again. And that's why merge sort is n log n, and this algorithm hopefully isn't. But there's something fishy, maybe, it sounds. How can you possibly do this second step? That sounds where the magic is happening. So that's where we'll use that we're sorting suffixes and not arbitrary strings. But let's first analyze the overall algorithm. Why does it make such a big difference that we don't recurse on the entire list? Probably I've seen this in master theorems, etc. But I want to just give the graphical representation. So the total cost, if we okay, I should have said this first. We will show that the steps 2 and 3 take linear time. They take time that is proportional to the length of the current list. And this will keep us busy for a while, but let's take it for granted for now. Then the total complexity of the entire algorithm is what you need in the first step and what you need in all the recursive calls. And so for the first step, we have a linear contribution from the steps 2 and 3. And that is for the entire list. So that's the topmost recursive call. And then we make a recursive call on 2/3 of that list. So that's something like this. That's the next recursive call. And that again has a contribution that's linear in that size. And then you do this one more time. And you keep going. Now at some point you reach an individual, just a singleton, and you stop. But this is, if you always lose think I should draw it slightly more carefully, maybe. If you always lose a constant fraction in the recursive call, what you get if you spell it out is a geometric series, or it's upper bounded by a geometric series. And the sum of these things, a number less than 1 to the I summed over all I, that's bounded by a constant. So in this case, it's bounded by 3. Okay. And so the overall running time of this algorithm is linear. That's something you will have seen for other algorithms. Quick select is similar in a sense. What are other typical algorithms where it just recurs on one side? Yeah, there's other examples. It'll come back at some point. This is a fairly standard analysis. The interesting part is showing that the steps 2 and 3 have linear time. Okay. Is the derivation here roughly clear how we get to this, the recursion? You can spell it out as a recursive formula. I've immediately unrolled it and then upper bounded. Okay, so what we still have to do is look at these 2 steps. How can we do those in linear time? One point that I glossed over here is we compute R, the rank array. At the end, at least, we want L, the suffix array. But as I claimed on the last slide already, you can always, if you have one, compute the other in linear time by just filling the array, iterate over the one and fill the other, jumping around. So we can, in the formulation of the algorithm, I'll allow myself to use L and R whenever it's convenient. And you can always, at the beginning of each step, compute the other one if you need it. So now let's look at step 2 first, which was we have the recursion done for these suffixes that start at positions 1 or 2 modulo 3. And we would like to sort these suffixes that start at multiples of 3. And we somehow have to use the knowledge that we got from these ones, from sorting those ones. So how could we possibly do this? And the answer is, let's start the obvious. If we want to sort these suffixes, we could start comparing and do some sorting method that works on pairwise comparisons. We can't afford to compare long suffixes character by character because they can be linear in the size of the text. So this would take linear time for just a single comparison, and we want to sort the entire list. But after we've removed from a suffix one character, if it previously started at, say, position 3, if you take off the first character, let's maybe do this. So if that is T3, if I remove that first character, what I'm left with is T4, the suffix that starts at position 4. And 4 is not a multiple of 3, so that's a suffix I have in the list that I've sorted already. If I compare T3 with T0, and also chop off the first character, I'm left with T1. This game again. And those two I can compare by looking at their ranks. So T1 comes before T4 if and only if it has a smaller rank in the rank array. So if R12 of 1 is smaller than R12 of 4. Okay. So we have the following statement that we can use. For any 2 suffixes, it's spelled out for this example, but it works for any index that's a multiple of 3. This one comes before this one in lexicographic order, if and only if this pair comes before this pair in lexicographic order, which means we start comparing the first component of the pair, which is a single character. That's this first character that I just deleted. Now for sorting, I can't simply delete it and ignore it. I have to look at it. But this is a constant time operation. Either those two characters are different, and then the one that comes earlier in the alphabet determines which of the two strings comes earlier in the sorted list, or they are the same, in which case I have to go to comparing T4 to T1. Is that idea clear? So you look at the first character. If they're equal, you have to continue. But if so, the remaining suffix is one that you have already sorted. And so you can reduce the problem of just sorting these pairs. Let's see an example on a slightly bigger text that illustrates this. So we have this lovely text, Hannah Bans Bananas Man. And it's convenient to add a few more dollars at the end so that we don't run into comparisons of something with empty. These are all the suffixes that start at a multiple of 3. So these are the ones that we want to sort now, and we don't know yet how their ranks are. And these are all the other suffixes, those that start at not a multiple of 3. And those we already have sorted. So here's, in text order, here's the sorted list, the suffixes in sorted order. And here, well, it might be small to read. If you have good eyes, you can read this is the rank array. And so it's listed so that the ranks are 0 up to 14 because they're sorted here. But of course, you could put that rank on the other side. Then it's just an array. Okay, so we know all the ranks for these suffixes that start not at a multiple of 3. And now we reduce this list of strings, which is tough to sort, to something that is efficient to sort, namely a list of pairs, or short strings if you prefer. And what we do here is we take the first letters. You see that this row of first letters is the same as above. It's just copied down. And then the remaining part here, so in this example of T15, the remaining part is just S-man and dollars. That is T16. So we go into our list and look up what's the rank of T16. And the rank of T16 here is 14, because it happens to be the last in the sorted order among those others. And so we replace this long suffix with just its rank. And so that brings us to this list. And sorting this list gives us the same order as sorting this list of suffixes. How can we sort these in linear time? Because they are short, we can use, and they don't have a big range, we can use something like counting sort that we've seen in Unit 3. That was this algorithm where at the time I told you keep this box in mind. We can sort these pairs by 2 iterations of counting sort. In the first iteration, we sort by the last component, and these are literally numbers, the ranks here. And then in the second component, in the second run, we sort by the first character of the pair. And that's characters, but we can always reduce the alphabet to all the characters that occur, and so it's never more than the number of strings in the list. Okay? So in a sense, using the single method we've seen for sorting in linear time is what we do here. We reduce the problem of sorting lists of strings to something that is a list of pairs of integers. And so with 2 rounds, we can get this done in linear time. And then we have the rank array for these. Now, I want to point out that the rank arrays, the R12 and R0, oh, here I did call it R0 instead of R3. I guess it's a mistake on the first slide then. The rank arrays R12 and R0 are ranks within their subset of suffixes. So these are the numbers 0 up to 14. These are the numbers 0 up to 7. So they only rank suffixes from within the same group. Okay? But that was what we wanted for the second step. We wanted to sort the third of suffixes that we did not recurse on using the information from the recursive step. And now comes the last step of this algorithm, step 3, where we have the two sorted lists of strings, and we want to merge them into one big sorted list. So let's see what we have. In green, this is the list that we just produced. That's the multiple of 3 suffixes in sorted order. That's the one that we got from the recursion in blue. That's the suffixes starting at 1, 2, modulo 3. And now we want to merge them. What we'll try is use the standard merging method from merge sort like I illustrated it on the slide back then. So we just go through these runs and pick the smallest of each and try to compare them. And whatever comes out smaller goes to the output, and we continue. This is exactly what you've seen before. The only trick that we need is make this comparison fast, because again, it's strings. It would take us potentially linear time to do one comparison. We can't afford that. I already started this merge, and I want to show what the next step looks like. So these are the next potential candidates for the next output element. So we have to compare this suffix and this suffix. I started a bit later in the merge because I wanted to compare 2 longer suffixes. The first are always the ones that have lots of dollars, so they're not so interesting. So we've been successful with sorting the R0 suffixes by just chopping off the first character. So let's try the same trick again. So in this case, we have to compare T15 and T11. Let's try chopping off the first character. So T15 is a green one. Chopping off the first character gives us T16, and that's a blue one. If we do the same to T11, we go from blue to green. And that does not help us at all, because we can't compare green and blue directly. What we can is, if I have 2 blue elements, I can look up in the sorted list which comes earlier. If I have 2 green, I can look up in the sorted list which comes earlier. But if I have 1 green, 1 blue, I don't know which one's better. So it looks like this doesn't work here. We still can't compare these suffixes that we got after chopping off 1 character. That's a bummer. But we can do it just one more time. If we chop off a second character, we're guaranteed to succeed. We can have a look at that in a second. So if we do that to the example, we take the ones that we were left with, 16 and 12. If we chop off another character, we get 17, which is blue, and we get 13, which is blue. And so I can sort those 2 by looking up where they occur in the blue list. So in this case, the rank of 17 is, well, whatever that is, 13 comes earlier. So 13 wins, and that should be the next one that goes here. Did I put that here? No. Let's just spend a very brief moment thinking why 2 steps should always succeed. That might not be quite obvious yet. But if you draw the array, it becomes clear. So let me color those like they are in the picture. So we have blue and green in between. And in a sense, we have to go through 9 different cases. The first run can start at 0, 1, or 2 modulo 3, and the second run can start at 0, 1, or 2 modulo 3. But many of these cases are boring. If they both start at 0, that actually never happens because we're merging 2 lists where this never occurs. So it can only happen that we have 1 green, 1 blue. And it's really just 2 cases because there's 2 types of blue. There's those that start at 1 modulo 3, and those that start at 2 modulo 3. And we have the case here where 11 is 2 modulo 3, right? And so the other case, maybe I can, yeah, so we have 0 mod 3 versus 2 mod 3. That one we have already done. That's one, the example down there. And then we can only have the one other case where we have 0 versus 1. So 1 is here and 1 is here. Oh, come on. Now, if we chop off one character, we move this arrow 1 to the right. So we jump to this one, and they're both black. Blue. And because they're both blue, we can compare them. Okay. So that's the one other case that we have to check. So no matter which two runs from green and blue you're trying to compare, if you chop off 1 or 2 characters, you always know you end up with 2 suffixes in the blue range. And so you can take the rank array 1, 2 to check which one comes earlier. So in total, you need constant time for each of these comparisons. It's chopping off 1 or 2 characters, and you can compute with the indices modulo 3 which case it is, and then maybe look up one comparison of ranks. So each step of the merge takes constant time, and merge overall uses a linear number of comparisons. So that together means we merge the 2 lists in linear time. Okay? As I said, both of the steps are a little tricky, but there's no huge quantum leaps in either of them. It is using, in a smart way, the fact that we have suffixes of a given string.